the aim of this talk is to connect maximality in set theory to standard notion of model theory, which is that of model companionship. In particular, we see that generic absoluteness results are related to preservation of phi1 theory, and model companionship results are related to forcing axiom and large fragments. Okay, so last time I introduced this signature. So epsilon delta 0 equals P delta 0 property and union the rudimentary function union the Gödel operation. And the point is that when you have a delta 1 concept, you can freely add to the base theory is Zf minus delta 0, which is equal to replacement for quantifier free formula. Actually, it would be better to use collection, because replacement is a bit weak, but for the purpose of our use of it, it suffices. And then all axioms except power set. And CFC minus delta 0 is CF minus delta 0 plus choice. And okay, and CFC.
Last question. Something which bothered me a little bit last time is that when you say delta 0 property, of course it is completely clear what it is. It is, you have to look at phi, and if it's delta 0, it is. If it's not, it is not. But some things are provable delta 0.
Yes, that's the point. So you have, what is this theory? I didn't say it explicitly. So what is this theory? Is the theory of this asta plus and sorry here.
Change. Put it into the.
No, use the from box.
From box. From the box.
Okay, so that's done.
Yeah, it's done. They will be used tomorrow.
Okay, so you have to add those axioms, the axiom that tells you the meaning of this formula, so of this new predicate, in accordance to what you expect the meaning to be. So you have to add an axiom, and what I will do, so if you check this axiom, all these axioms will be expressible by pi2 sentence. Even choice will be a pi2 sentence. The unique one problematic will be the power set axiom that will be a pi3 sentence. Okay, and the theory, the base theory is saying, for example, that the predicate for all x p of y1, yn. So you have to add one has to add the statement for all y1, yn. Rp plus R for all x P of well, let's leave it like this, otherwise I would have too many y1, yn, if and only if for all x this is, I didn't put the bound, but so I want bounded. So for all x in z, so it's for all y1, yn, z, and z, y1, yn, if and only if x in z implies p of x, z, y1, yn. Okay. So you see that in this way we are saying And actually, this is bad because in this way I'm using the formula of arbitrary complexity, but okay. So in this way, you see, this is a Python sentence because um, this is a quantifier free. Actually, it is atomic. This is atomic. This is an implication of atomic formula, so it's quantifier free. I'm doing a universal quantification, double implication. So this is essentially, in this direction is pi 1, and in this direction is sigma 1. And here I have the universal quantification, so it gets pi 2. Okay? So, and using this trick, well, now all the delta zero concepts are get the intended meaning, and you have to add similar action for the rudimentary, and you can check that they also have sigma pi 2.
So why do you have both rudimentary and error questions? Because to me they are like alternatives.
Yeah, and the point is, I want to have as many as needed.
Oh, I see.
So I don't want a minimal axiomatization. I just want a recursive axiomatization where when I want to pick an absolute function, I can put it in. So for example, it is very convenient to add also a predicate for the most often collapsing or something like this. I mean, provided it is an absolute constant, you can put it in.
That's pi 1, no?
What?
Oh, you can only, yeah, okay.
Okay, so
You're happy as long as you get pi 2.
Huh?
You're happy as long as
Yes,
you get pi 2.
yes, as long as it is pi 2. So you see, with this, so this theory, with all these other axioms that I need to give the right interpretation to is the pi 2 theory. Okay? And still, I want to make another comment on this. Yes, the other fact is this: if C is delta 1t, so C of x is delta 1t, and P, let's say T1 z equals Tjz equal y is also delta 1t for all j equals 1n, then C of T1 x Tn x. So here I'm a bit floppy because each one has its own arity, so you might have to change but modulo some syntactical polishing is the delta 1. Okay, so composition of delta 1 properties is still a delta 1 properties, which essentially means that you can really add these predicates to your theory and you're not going to change what is the absolute between substructure of the theory. Because those properties will go upwards as they are sigma 1 and they will go downward as they are phi 1. Okay, and the other point is if C is delta 1, C x is delta 1t, and t extends the minus delta 0. And theta is defined, theta x is defined by transfinite recursion over Cx. So you have certain property and you use this property to do transfinite recursion over it. You end up with the theta x is still delta 1. So this is saying you can use freely induction and composition to propagate the effect of being a delta 1 property in this theory. Okay. So here again I'm sloppy, but for example, suppose you do the Mostovsky collapse. The Mostovsky collapse is making a transfinite recursion over the epsilon relation. The epsilon relation is delta zero, and you get that the Mostovsky collapse is okay. And so essentially this is saying, okay, this theory is pi 2, and it is already very good because essentially every delta 1 concept that we are used to study in that theory is expressible by a delta 1 property, probably in this theory. Okay? And this is the base theory for doing set theory, and then on top of it we add the other predicates. And the predicates we will add are A contained in, let's say, 2 to the omega to the n, such that A is universally curved. So sorry for my notation, which apparently is not standard. And n omega 1. And okay, then we still have one notion from model theory that I used last time, that I introduced last time, which is the definition given tau theory T, M is T is T if for all n which are superstructure of M is the sigma one elemental in n, and there is n which model there is one such n. Okay, and the other remark I made, but it's not, well, it's never complicated proof, but maybe not trivial argument, is that if M is T, then M models C for any pi 2 C such that C plus T for all, sorry, this is not, this was a bit sloppy. MSTS, let me do it like this because this is how I'm going to use it in the remaining talk. And pi 1 complete means every universal sentence is either decided by T. So there's no confusion about what is pi 1 truth. The incompleteness may arise just at higher levels. Okay. And then this is the case T for all, this for all suffice because there is no possibility of extending T for all. T for all. So what is this? It is C is Boolean combination of pi 1. Okay. So what is saying this observation? It is saying if you have a pi 2 sentence, in order to check that the pi 2 sentence is true in this existentially closed model, you just have to.
What is larger? Yeah, like a T for all. Or
Exists.
is it?
Is it like, is it?
Yes, apologies.
Okay,
Apologies. I'm like a student. You understand this symbol, but not the other one. Okay, so this is saying,
I
in
mean, it's
order
one of the conjectures.
Huh?
It's one of the conjectures. I mean, one of the conjectures is a typo.
This is- Okay, so it is saying you want to check a Python sentence and see if it is true in this model. You just have to check that it is consistent with the universal and existential sentence. If this is the case, then it is true in this model, and actually you can check that C such that M model at C for all T M is well, if you look at this, so this is the theory of existentially closed model, and you look at the Phi2 fragment of this theory, this is exactly this one. So it is equal to C such that C is C plus T for all well exists is consistent. C is okay. So so what happens with these existentially closed models? They give a notion of maximality for Python sentence. They say if the Python sentence is consistent with the universal and existential sentences, then you know that it's going to be realized in an existentially closed model. Okay, and this sounds very much like forced in axioms or star, because star, what does the equivalent characterization of star says? If a Python sentence is forcible by some forcing, then it holds in the star model.
Sentence they say, you have problems to T, and M is T existentially closed, if for every N, and there is one such N.
Yes. So there is a superstructure which models T, because otherwise it would be backwards reading the universal quantification. And then, provided that there is the one superstructure that is the model of T, any superstructure which is the model of T is the model of is the sigma one superstructure. So you will be able to reflect back. Okay. And then the problem comes. There are even complete. There are complete theories. S such that the class of SEC models is not elementary. Okay, so this is saying, okay, I have this very nice notion of existentially closed model which captures the Python content of well, whatever is given a Python property. If it is consistent, it will hold in this, but maybe this class of existentially closed models are badly axiomatized, so you cannot find a theory that axiomatizes them. Okay? And the definition or theorem, let's say, definition has as T as its model companion. If M is as existentially closed, if and only if M is a model of T.
Are there many ends which?
Huh?
How can you say that n is unique? I mean, there are many ends, no?
Yes. No, I just say there is at least one which is a superstructure.
I said there is. Oh, there is at least one. That's what it says.
Finish.
Oh, and there is at least. Oh, okay.
Yes, so.
I thought you said there is unique. Okay. Okay.
So the point is the theory is nice if the theory of its existentially closed models is the existentially closed models define an elementary class. Okay, and that's the notion of having a model companion. And when this occurs, so theorem has a model companion. If and only if and only if T is T is equal to its Python fragment, okay, and what else is the point? And
Extensively closed models is
yes, this is saying existentially closed models are an elementary class. And T is axiomatized. Sorry. T proves that every universal C is T equivalent to an existential. That means for all, if you have for all x C x Z with C quantifier free, you get that there exists theta C y Z with theta C quantifier free, such that for all Z C x Z, sorry, for all x C x Z, if and only exists y theta C y Z yes is in T. Okay. So this is what I'm going to use to prove this fact that you can axiomatize by Python fragment the existentially closed models. You are in the very nice setup where you can prove that every universal sentence is equivalent to an existential. Okay. This is one of the possible. This last property. So this fact that you have a theory where every universal sentence is T equivalent to an existential sentence, this is called model completeness. It's one of the possible characterizations of model completeness, and it's the one that we're going to use. So what happens with this type of theories, they are making all the concepts delta 1. Okay. And they have the very nice feature that you start from the theory S, you get the existentially closed models. When you are able to do this and find that these existentially closed models define an elementary class, this elementary class is very canonical in the sense that it has a Phi-2 axiomatization that is telling every formula is equivalent to every existential formula is equivalent to a universal. model theoretic background. And also the other very nice feature of this model companion theories is that not only all the delta 1 concepts, all the concepts are delta 1 with respect to the theory, but they are also maximizing the pi 2 family of statements that are consistent with the universal fragment of the starting theory. Okay? And now let's make some basic remark, observation. Theorem. Please. If P is n-forcing, H alert 1, epsilon delta 0 is elementary H alert 1, or let's say, well, it's better not elementary, sigma 1, H alert 1. Okay, and Wooding class many Wooding. Here you put full elementality. Okay. For any the theory of HLF1 is the fully elementary in the theory of HLF1 and computed in the generic extension. Okay, so this is the first indication that this structure looks like an existentially closed model. Okay. Because you cannot use forcing to produce superstructures which are not such that the sigma 1 properties are not reflecting on it. Okay, so the question is the theory in this signature epsilon delta 0 model complete? So model complete means for me this so every universal sentence is equivalent to an extension set. And the answer is, do you have a guess? So is every, so what are universal sentence? Universal sentence are pi 1 2 defined, pi 1 2 sets, essentially. H omega 1. So here we are saying, is every pi 1 2 set equivalent to a sigma 1 2 set? And the answer is
No.
no.
We collapse.
So the problem is that, well, the obstruction is that the projective sets are increasing in logical complexity, so they are not stabilizing. So if you want to make this model complete, you have at least to be sure that the projective sets do not increase the logical complexity in your theory. And that's where your notion of universal reverse starts to pop in.
Is this essentially the same as the theory of the reals?
Yes, this is the same as the theory of the reals, but you have to put one quantifier more. So the sigma 1 properties here become sigma 1 2 properties when you move to the reals. Okay, and observation, it's not really a deep theorem, so let's call it lemma. Lemma.
Okay. Yeah, okay.
Assume A contained in the power set of the power set, well, to be precise, we have to allow all n's. So union for n in omega of power set of 2 to the omega omega to the n. Okay, so each element is, so essentially, that I don't know if you put the right type, so let me write it. Assume for all x belonging to A, there exists an n, x is a subset of the power set of 2 to the omega to the n. So, no, to the n. So it's a set of tuples of real numbers, yes. So it means that each element in X is n tuple of real number. Okay. And if X in A, projection on the I coordinate of X remains in A, and if X, Y belongs to A, X intersection Y belongs to A, well, if they have the right arity and complement of X. Okay, and A, okay. So we have a family which is closed under projection, under complementation, under intersection. So for example, the projective set of fields. Then the theory with these extra predicates is model complete.
But that's essentially like cheap version of normalization, right?
Yes. Yes, H omega 1 epsilon delta 0 A in A.
And then that's cheap of the refined.
Okay. So you see now this is connecting very nicely with the Woodin and Shirkin results. It says, okay, provided you enlarge the vocabulary, you are making your theory nice. But now you see every concept expressible in this language is the delta one. The problem is maybe you make it too nice, too large. So you have added too many predicates. Some of them are wild, are not controlled by forcing. So, for example, if you stay inside the realm of universal reversal, it's okay because then you go to forcing extension and you have a canonical interpretation of this predicate in the forcing extension. But if you go out of the realm of universal reversal predicate and here you pick something that is wide, defined using the axiom of choice, you go to the generic extension and you don't know how to interpret this, and you may use this elementality property. So this is saying, okay.
So we assume many.
Yes, plus many. Or, I mean, no, this result holds true trivially in CF, even without choice. Okay? This is saying, if you are taking a family of.
But you get more of completeness.
Huh?
But you get close.
Yes, I get model completeness, but the problem is I want to pair two things. I want to pair model completeness with the fact that if I go to a forcing extension, then I'm a superstructure. Okay? And here, if I have a wide predicate, I go to a forcing extension and I'm not anymore a superstructure because the wide predicate I don't have a canonical interpretation. Okay? So, corollary is that if A contained in UB and well, the UB sets are always the satisfied assumption of the lemma. That is when you are talking in the last cardinal function of lemma. The theory of H omega 1, epsilon delta 0, A in A is model complete. And generically invalid.
So it could be just projective sets.
Yes, it could be projective set, it could be all universal set, it could be something in between.
So, but still you need the classical universe.
Well, if I take just projective set, I think it suffices counter the many Boolean and the measurable stuff.
Oh, okay.
Okay. And you see why now this is very nice, because now this is saying, okay, I have a type 2 statement, and if I can make this true in the, or even a sigma 2 statement, or whatever statement, well, the type statement that was, if I can make it true in the generic extension, it will be better.
So it says model complete and generically absolute in B.
Yes. Is model complete? This is an absolute statement. This, yeah, okay. But generic absoluteness. So this is saying, how do I check that the Python sentence is consistent? Well, is realized here. I just have to go to a forcing extension and check that it is realized.
So getting consistency is.
Is the same as the possibility. So you see, it becomes probability in this model companion theory, in this model complete theory, overlaps with the consistency with the universal fragment of set theory, and overlaps with forcibility over a model of set theory.
So with respect to this theory, there is no other method.
Exactly. Exactly. So you are identifying a canonical class of statements, these Python statements that goes here, that are essentially those that are consistent in some way with set theory, or those that are forcible over set theory. Okay. And you see that here it is very easy, because already Bartosz guessed correctly what was happening, essentially to get the model completeness. Essentially, you know that every set is coded in an absolute way by a subset of the reals. If the sets that you can define are coded just by universally per set and just close under projection, the absolute coding allows you to transfer the definition of the set into a definition that talks about the universally per set of by which it is coded, and that is a sigma 1. You can check that it is a sigma 1 definition or a pi 1 definition. Okay, and now we want to do the same stuff for HRF2. And here there are some more difficulties to match. So this is what I should do.
Change.
Let's see if it works. So let's, no, it still works. Okay, so I want to do now the same with the HRF2. Okay, and here we will have two problems. First problem is to check the preservation of pi 1 theory across forcing extension. because this is the basic ingredient to have the hope that forcibility overlaps with consistency for this Python sentence. If this is false, there is no hope that this matching occurs. Okay, and the second is which kind of predicates do I have to keep to add inside to get this model completeness. So I will have to put in enough predicates so to be able to prove that every sigma 1 formula is equivalent to a pi 1 formula, but not too many to lose the fact that if I go to a forcing extension, I lose the pi 1 preservation of the theory. Okay, so this is the first non-trivial result. Theorem. Assume class many Boolean. Let P be any forcing. So this forcing could collapse omega 1, for example. Then the theory of H are the two, well, actually the theory of V. The universal theory, let's say universal extension theory for V, epsilon delta zero, NS, A belongs to UB, is equal to the universal and the extension statement of VP epsilon delta zero minus VP A VP A belongs to UP.
So this A, B, B is the canonical.
Yes, the canonical translation. Yes. So it says, okay, if you force, maybe you kill what is omega 1, and you have to reinterpret in the generic extension omega 1, you have to reinterpret the notation idea, you have to reinterpret the predicates for universal perspective. But even in this reinterpretation, the universal sentences that were true in the ground model remains true in the generic extension. Okay, so let's see that it's not unplausible. So, for example, in this language, we have that ZFC, the use exists as such that not NS S and not NS omega 1 minus S.
Of course, it is essential here that it is this universal extensor for.
Yes.
Like CH is not of that form.
Yes. CH is in this language. CH is pi 2. Not CH is pi 2.
Okay.
I will complete that. So this is saying there exists a stationary and non-stationary co-stationary set of subset of omega 1. In this language, it is sigma 1. It's provable from VSC, so it's clear that it is a couple reserved. Okay? And let's see a problematic one without Nash cardinal.
That's a choice. Oh, but you're not assuming that.
No, but the point is the Boolean combination. No, I'm assuming class many Boolean on top of VSC.
Okay. But doesn't that simply follow from the axiom choice?
Yes, but it means so now the meaning is completely different here and here.
Oh,
I'm just saying it's not implausible. You have this statement, which is a non-trivial sigma 1 statement, holds here and holds here.
Yeah.
Okay, and here is one that says that you have to put Nash cardinals inside. So omega 1 of V equals omega 1 of L. Okay, so again, this is, you can check that this statement is expressible by a delta 1 property, and it's not upward absolute if you work in, if you start from V equals Z. Okay, it is true in the ground model, but you force to collapse omega 1 to become canonical and it becomes 1. Okay, so this theorem, this is saying, in order for this theorem to be true, you need Nash cardinals. And most likely not much less than what is in this assumption.
It's also, it means, so there's a kind of, well, that if you can, by forcing, get something, and that's kind of it, that's a statement, and you can get it without force.
Yes, it's already saying this for existential statements, but I mean the relevant one of the type for existential with parameters, and so let me prove what time is it? Do I have time?
15 minutes.
Okay, then it's
So the first.
so proof. And now we combine a bit of stationary tower and a bit of PMAX technology. Proof, let C be sigma 1 and assume B model C. Let G be P generic for P and H be B generic for, let me use this notation, but in Larson's book this is Q delta, countable stationary tower that concentrates on countable sets with G belonging to BH. Okay, so since I have plus many Woodin, I can go on top of G and force with so that I have this equation. Well, then since also I have plus many Woodin, let apologies, I have still to make some VG generic for P. And I suppose that I go 2 Woodins above G. Let H0 be VG generic such that VG H0 models NS is precipitous and VG H0 is an SSP extension of VG. Okay. So what have I done? Well, I started with V. I have gone to a forcing extension where maybe my sigma 1 statement is now false. I have the phi 1 statement too. And now I go to a, well, the problem of this forcing extension is that it may have a very bad notion of non-stationarity. So I go to a further forcing extension where now the non-station ideal is nice. Okay, and let gamma less than delta be such that V gamma G H0 models ZFT. So for example, gamma is some large inaccessible.
Or delta is one of your OIDs or
Yes. So and what happens in this setup is that this becomes an iterable condition in the generic extension. In VH, V gamma G H0 is iterable. Huh? No, gamma is smaller than delta, but I can put on top. I mean, if I put all the initial segments up to delta of V gamma are and
You said gamma G doesn't have maybe G intersection or something?
so this is I mean gamma is inaccessible in VG gamma in VG. So V gamma G is the interpretation of the
Oh, this is but it's not really V gamma G, right? It's VG sub gamma.
Yes, but it's the same because gamma is much larger than the size of G, and so the interpretation of all,
Oh, G. G looks like
I mean, huh? No,
oh, H
G is
what-
small.
oh,
H
sorry.
of size delta. G is small.
Okay.
So this is a small countable transitive structure, and it's iterable because it is an initial segment of VGH0. Okay. Let J be an NS product iteration of B gamma GH. Which belongs, J belongs to U.
So you consider it as a P-max condition,
Huh?
iteration as a P-max condition. P-max condition.
Yeah, it's the first component of the P-max condition. Now I made this B gamma.
Was there a room below delta?
Yes, to be on the safe side, but maybe I think you don't really need because you just need precipitousness. So maybe measurable surprise or in order to make, I don't know if you can move by stationary set preserving forcing precipitous without the Boudin. Okay. Okay, so there is a Boudin below delta in order that you can do this stuff. Okay. And now you iterate, and now what happens is that VGH0 models not psi. That was our working assumption contrary to hypothesis. And when we iterate this up, and not why? Well, VG, the model is not psi. I forced with an SSP forcing to get to H0, and I didn't change the meaning of non-stationary ideal. So the notion of stationarity for what that was was the same. And apologies, maybe I should start with the opposite situation. So with pi1. So suppose I start with a universal sentence, I make it false. Here, okay, VG model not C, so this is now an existential sentence. I maintain that it's false here because I didn't change the meaning of the non-stationary ideal and of being, well, the universal reverse set I can always reach, but the meaning of non-stationary ideal is, I mean, they have the state one, and on the stationary set that are in VG and VGH0 agree. Okay, so if there was a witness for this for this existential sentence in VG, the witness remains such in VGH0. So we also have that this is true here, and now this is an iterable pair. Okay. So this means that J0, so let's call it M0, J0 omega 1 BH.
Something to check, no? This is psi is psi 1, so psi not psi is sigma 1.
Yes,
Sigma 1 with the UV set in B. Right?
yes.
Don't you want to show that there's some element right when we go to the extension?
Hmm?
Is that true? With MS as a predicate.
Yeah, the point is So here there is, in this side, there is some universally variable V, which are appear as a predicate.
And that's also.
And S also appears. So NS and psi appears. Okay. Then here I interpret completely NS. So there's no relation between the NS of the ground model and the NS here because I have collapsed omega 1, whatever. But I have a canonical interpretation of the universal reverse set appearing. And the point is that this condition is iterable for any of its universal reverse set. So whatever universal reverse set appears here, it is a issue.
Why is BG zero satisfied now? Not
Because it's a SSP extension of BG. So I didn't change. So now BGH0 and BG agree on the omega 1 and agree on the notion of stationarity. So it's actually BGH0 is a superstructure according to this signature of BG. So with respect to this signature, it is a superstructure because it's an extension by a stationary preserving force. So it has the same non-stationary ideal. I mean, the non-stationary ideal is larger, but it agrees with what was seen by BG. Okay. So the sigma 1 property that was true here remains true here. Okay.
things just.
Because the point is that with respect to this signature, BG and BGH0 are one substructure of the other because I didn't change the omega 1 and I didn't change the fact that the set is stationary in BG if and only if it remains stationary in BGH0. Okay? And now this is iterable for whatever, sorry, it's better to say, is A iterable for any A belonging to UP BG H0, but actually I just care about those that appear in A in UPV because those are those that can appear in this formula. Okay, so I get that J M0 models not C, but note that let's call this M omega 1. So and now note that M omega 1, well, this is a bad choice because there's ambiguity of what is omega 1, where am I looking at? So let's call it that. And delta, epsilon delta 0, A and delta, A belonging to UP of B, is a substructure of VGH. Sorry, VH. Yes, VH. Epsilon delta 0. A VH. A belongs with P. And sorry, here I also have to put the non-stationary field. And also here. Okay. Why? Well, because the iteration is correct in the generic ultrapower. Well, let's say that J belongs. Let's make it here. It doesn't really matter. Or should I leave it? No, maybe it's better. Sorry, apologies. J belongs to B. Okay, and here I should check that. This is okay. B G H0, and here apologies. I take I see that this is iterable in the generic extension, so it's also iterable in the ultra power. I iterate in the ultra power in a way that it is correct, so that this is interpreted in the correct way, and the others I know by automatically that they will be correctly listed. So I have now this, and here this is modeling not psi, which is sigma 1, and this is modeling psi by elementarity, which is pi 1, and it's impossible that a sigma 1 statement is killed in a superstructure. Okay? So I get a contradiction. And one can do a similar trick if you started with a sigma 1. Well, it's a bit, there are, so what you do, well, you take the negation and you run this argument with the negation. Okay? So I think it's